Chapter 31, Electromagnetic Oscillations and Alternating Current. Check out this video from Lessix. This is one of my favorite YouTube channels, The Physics Behind Engineering. This video addresses the most fundamental aspect of oscillating circuits.
If you connect a charged capacitor across an inductor, you will see a beautiful energy exchange take place between the two elements. These energy oscillations look as if the capacitor is saying, "You take the energy," and the inductor then says, "No, you take my energy." Why don't any of these elements store the energy and become settled? Let's have a look at the interesting physics behind these oscillations and some of the applications. Before diving into the LC circuit, we need to understand a simple circuit, a capacitor-resistor circuit. The capacitor is fully charged initially. Let's introduce a resistor into the circuit. Here you can observe that initially the current flow is at the maximum and then it sharply decays with time. This is expected because at the beginning the charge difference is at the maximum, so the current has to be at the maximum. Now let's see what will happen if the resistor is replaced with an inductor. Here again, the capacitor is fully charged initially. It's quite logical to expect that there will be a huge current flow at the beginning, and then the current flow would reduce as in the previous case. However, this will not happen in practice. An inductor develops EMF across it, based on the change in current flow. This means that a drastic change in current is not possible across the inductor as in the previous case. Now the current flow starts from zero and increases to the maximum, and then comes back to zero again. In an inductor-capacitor circuit, the current flow variation has to be gradual, and here we can see that the current flow in the LC circuit is shaped like a sine curve. Let's look at the electron flow animation once again. The current in the circuit starts from zero and gradually achieves the maximum value. In the next 1/4 of a time period, the current from the capacitor starts to decrease, resulting in another change in current. At the end of the capacitor discharge, if you check the EMF across the inductor, it will have the opposite polarity to the initial EMF. This reverse EMF charges the capacitor with the opposite polarity. In the next half of the time period, the capacitor will be fully charged with the reverse polarity. This also means that the current flow will be in the reverse direction for the next half. Hence, in an ideal circuit, this back and forth flow of current would continue to charge and discharge the capacitor and form endless oscillations of energy. However, practically, we can never achieve such ideal behavior due to the presence of resistance. The resistance causes energy decay in the form of heat. This means that in a practical circuit, the oscillations will die out eventually. As we increase the resistance, the oscillations die out very quickly as shown. If we increase the resistance further to some critical value, there would be no oscillation at all. Underdamped LC circuits have many applications in industry, namely thyristors, magnetrons, etc. In communication systems, they are an integral part of frequency filters. Please don't forget to support us. Thank you.
Here's a great visual graphical representation of an LC circuit. Energy is oscillating between stored electrical potential energy in the capacitor and stored magnetic potential energy in the inductor. Fight the good fight and go through each and every one of these steps. This table breaks down in a lot of detail each of the 8 steps that occur over one complete cycle. As you go through this table, make sure you keep referencing this visual. In step A, we start out with a completely charged capacitor and uncharged inductor. All of the energy resides in the electric field between the capacitor plates. In step B, you see the capacitor begin to discharge. The red arrow shows conventional current direction. As this current flows through the inductor, a magnetic field forms, and the energy is split between the electrostatic potential energy of the capacitor and the magnetic potential energy in the inductor. In step C, the current attains its maximum value, the capacitor is completely discharged, and all of the energy resides in the magnetic potential energy in the inductor. In D, even though the capacitor was completely uncharged, current continues to flow counterclockwise because the inductor wants to maintain this counterclockwise flow. This is the inertia of the inductor. This continuing counterclockwise flow gradually deposits positive charge on the capacitor's bottom plate. We once again have a mix of electrostatic potential energy in the capacitor and magnetic potential energy in the inductor. In E, the cycle is halfway completed. The capacitor is once again fully charged, but the polarity is reversed. All of the energy resides in the electric field between the capacitor plates, and the inductor is completely de-energized. Going from step E to F, G, H, and back to A completes the full cycle. The second half of the cycle is just like the first half, only in reverse. In the absence of any resistance, this cycle would repeat endlessly. An LC circuit is an oscillating circuit, and it's also sometimes referred to as a resonant circuit, tank circuit, or tune circuit. This entire page is review. Make sure you go through it from top to bottom. Understanding all these details really does make a difference. The one blank you can fill in is right here. Omega equals 2 pi f equals 2 pi over t, where omega is angular frequency, f is frequency, and t is period. You've used this a lot in many previous instances. In fact, the next section is titled Mechanical versus Electrical Oscillator Analogy. On the left is a simple spring mass oscillator. You've studied various aspects of this system's simple harmonic motion in a previous chapter. An LC oscillator is very analogous to a spring mass oscillator. They are both simple harmonic oscillators. Take a lot of time and study this section. It's the basis of the differential equations that apply to oscillating circuits. For the spring mass system, we use Newton's second law and calculus to arrive at a solution for the position function. We also got this expression for natural frequency. Omega is the square root of k over m, where k is the spring stiffness constant and m is the mass of the oscillator. In the oscillating circuit world, our defining equation is Kirchhoff's loop rule. We take the exact same approach and get a solution for the charge function and also for the natural frequency of an oscillating circuit. Omega equals 1 over the square root of L times C, where L is the inductance value of the inductor and C is the capacitance of the capacitor. Again, take some time to incubate on all of this. It really is helpful to see two different systems side by side. Box 2 provides a brief recap. We use the same calculus approach to get the charge function and an expression for angular frequency. This is used a lot. Here's our charge function Q. Here's our current function I equals dq dt. And here at time equals 0, we see the first reference to phi, which is phase shift or phase angle. Phase shifts and phase angles play a really central role in this entire chapter, so make sure you pay special attention to any reference to Greek letter phi. So here's our updated expression for the charge function and the current function. Here are some very informative graphs of charge versus time and current versus time. Remember, any reference to charge is referring to the charge on the capacitor. Inductors don't store charge. Notice how the charge function and current function are out of phase by 90 degrees. In an LC circuit, we have a sinusoidally varying charge function and current function, and thus also sinusoidally varying electrostatic potential energy and magnetic field potential energy functions. You can express the maximum electrostatic potential energy this way and the maximum magnetic potential energy this way. Because energy is conserved, they're equal to each other. Here's the graph of electrostatic potential energy. Here's the graph of magnetic field potential energy. Here's what you get when you add the total of both energies. You get a constant value that fluctuates between both energy types. So now we graduate to a more realistic situation. We're not going to ignore resistance. We are going to ignore electromagnetic radiation, which does rob energy from the system. This is something we can pretty safely ignore, at least at this point. We fully charge the capacitor with this EMF. We understand that the resistor is dissipating energy according to I squared R. We know that both electrostatic potential energy and magnetic potential energy are both affected by this loss, and we arrive at this differential equation, which looks remarkably similar to damped simple harmonic motion. Here's resistor, inductor, capacitor, also known as RLC, simple harmonic motion, and here's spring mass simple harmonic motion. Again, look how analogous they are. This is our updated expression for the charge function, and specifically omega subscript d refers to the damped angular frequency. The damped angular frequency is basically the same as the undamped frequency with a damping factor that's accounted for. Once again, completely analogous to simple spring mass simple harmonic motion, we have three kinds of damping for RLC circuits. I should make special mention of the term natural frequency. This is the frequency that the circuit would oscillate at if there were no resistive losses. If the term R over 2L is less than the natural frequency, we refer to that as underdamped. The circuit quickly reaches zero but oscillates around it like you see here on the graph. If this R over 2L damping term equals the natural frequency, we refer to that as critically damped. Critically damped means the system decays to zero in the shortest time possible with no bouncing above and below equilibrium. If this damping term R over 2L is greater than the natural frequency, we refer to that as overdamped. An overdamped system doesn't oscillate but moves more gradually towards equilibrium compared to critically damped systems. This is the rather complicated looking expression for the capacitor's energy decay. Here's an RLC circuit with a damping factor less than the natural frequency. You can see how everything gradually decays over time. This is just like if you were driving down the road in a car and you hit a speed bump and you're driving with a messed up suspension, so you end up bouncing afterwards for a really long time, which would be pretty irritating. Here is a critically damped system. The damping factor precisely equals the natural frequency. The circuit decays in the shortest time possible without going into oscillation. Control systems are often designed so the system reaches the desired state as quickly as possible without overshooting. Here's an example of an overdamped system. The damping factor is greater than the natural frequency. The system doesn't oscillate but moves more gradually towards equilibrium compared to the critically damped system. Okay, let's look at what happens when a resistor is connected to an alternating voltage source. This resistor is also known as the load and could be anything from a hairdryer to an electronic device to a light bulb. Our voltage source, or EMF, comes from this generator. The loop turns in a circle, which is why we get a sinusoidal signal. Here's our EMF. Here's the current flowing through the resistor. Here's the voltage drop across the resistor. Here's the alternating current form of Ohm's law for resistors, which looks pretty familiar. And here's the phase angle for a resistor's current versus its voltage. You can see the current going through a resistor is in phase or perfectly synchronized with the voltage drop across that resistor. This is where we introduce phasors, or phase vector. This graph is showing the current flowing through a resistor and the voltage drop across the resistor. As mentioned, they're perfectly synchronized. They're in phase, or phi, the phase angle, equals 0. This is a phase diagram showing the current phasor and voltage drop phasor on the same graph. By convention, these phasors rotate counterclockwise at this angular frequency, omega subscript D, which is the driving frequency of the EMF. You can see because they're in phase, the current phasor and the voltage phasor are lined up perfectly. Capital letter I subscript R refers to the maximum current amplitude. Capital letter V subscript R refers to the maximum EMF amplitude. At any point in time, the current flowing through the resistor is little I subscript R and is shown as a projection onto the y-axis. Similarly, for the voltage across the resistor, V subscript R is the magnitude of the EMF phasor projected onto the y-axis as well. This animation shows the phasor relationship between current and voltage for a resistor. You can see how the brown voltage phasor and the black current phasor are always aligned. there's no shifting between these two signals. You can see they both rotate in a counterclockwise direction, and that's convention. The length of these vectors corresponds to their magnitude or maximum values, and check out their projections on the y-axis. The magnitudes of those projections indicate the voltage value and current value at any particular time. Carefully study these summary bullets. They do a good job describing what happens with alternating current when only a resistor is present. Now let's have the exact same conversation about a capacitor in series with an alternating EMF. We once again start with Kirchhoff's loop rule, use the Q equals CV equation, remember the definition of current, and this box is very important. This is the reactance of a capacitor. It's basically the capacitor's version of resistance. This doesn't come from a physical resistance to charge flow, but rather an electrostatic resistance. Notice the dependency on frequency. The greater the frequency, the lower the capacitive reactance. There's also an AC Ohm's law for capacitors. Ohm's law is V equals IR, and for capacitors in an AC circuit, V equals I X subscript C. We need to talk about phase shift. Capacitor current leads its voltage by pi over 2 radians. This animated phasor diagram shows the relationship between capacitor current and capacitor voltage. Both the phasors are rotating counterclockwise, again by convention. And you can see that here for capacitor, the black current phasor leads the blue voltage phasor by 90 degrees. Once again, the length of both these phasors indicates the maximum value of current and voltage. And at any moment in time, t, their projection onto the y-axis indicates their values at that instant. Here's a good bullet summary and visual representations of the phasor relationship between a capacitor's voltage and the capacitor current. You can see via the sinusoidal graph and phasor diagram how the capacitor current is leading its voltage by 90 degrees. This also explains why we say current leads voltage in this case rather than voltage leading current, which is a legitimate question. Finally, we look at what happens when an inductor is connected to a sinusoidally varying EMF. Once again, we start with Kirchhoff's loop rule, and in the process of dissecting the loop rule, we introduce capital X subscript L, the reactance of an inductor. Once again, the unit is ohms, and this represents the inductor's resistance, which is like the capacitive reactance, not a physical resistance, but an electromagnetic resistance. Here's another AC Ohm's law, V equals IXL. Here, however, current trails voltage by 90 degrees. And here we have another outstanding summary of the current and voltage relationship for an inductor. Study the sinusoidal representation of inductor voltage and current, and also the current and voltage phasor relationship. Here's the animated phasor diagram for an inductor's current and voltage. The black phasor represents current and the green phasor represents voltage. They both rotate counterclockwise, which is the convention. Their angular frequency, omega subscript d, matches the angular frequency of the driving EMF, and you can see the current phasor lagging the voltage phasor by 90 degrees. Once again, the length of the phasors represent maximum values, and the magnitude of their projection onto the y-axis represents their value at a given time, t. Here's a very useful AC summary table. Go back and review all of the explanations that led to this point. It's really important that you understand every single step that went into constructing this table. Okay, now that we know what happens with a resistor, capacitor, and inductor when they are subjected to a sinusoidally varying EMF on an individual basis, let's put them together in series. This is the series RLC circuit. The source oscillates sinusoidally as shown here, and the current I is the same everywhere. That's kind of the master clock. No matter what's going on with the current through any given element and that element's voltage, current is always the same everywhere. For the umpteenth time, we're starting with Kirchhoff's loop rule. The first phasor diagram here represents the current phasor. Again, I think of that as the master clock. Now you're looking at 3 voltage phasors: the inductor voltage phasor, the resistor voltage phasor, and the capacitor voltage phasor, all on a single diagram. Start with the resistor voltage phasor. It is precisely aligned with the master current phasor because there's no shift between the resistor's voltage and the current going through the resistor. Notice how the inductor's inductor's voltage phasor is leading the resistor's voltage phasor by 90 degrees, and how the capacitor's voltage phasor is trailing the resistor's voltage phasor by 90 degrees. Once again, the voltage phasor for the resistor is completely aligned with the current phasor. Now we apply simple vector operations for each of these phasors. The vector sum of all three phasors always add to the maximum EMF. We can use simple right angle trigonometry to determine the circuit's phase angle. In this case, phi is always understood to mean the angle between the circuit current and the circuit voltage. In this case, once again, the voltage phasor for the resistor is a stand-in for the circuit current. Okay, here's a phasor diagram animation that represents all four elements: the EMF, the resistor, the inductor, and the capacitor. Go through this carefully and recognize the inductor phasor leading the current phasor, which is proxied by the resistor voltage phasor. And notice how the capacitor phasor is trailing the resistor's voltage phasor by 90 degrees. Notice that at any instant in time, the resistor, inductor, and capacitor phasors all sum to the series phasor. This is true if these were voltage phasors or resistance and reactance phasors. Okay, study this page really carefully and repetitively. Applying the Pythagorean theorem to the right angle triangle shown at the right, which is formed by phasors, we get an expression for circuit current, capital letter I, which looks a lot like Ohm's law. You have I on the left side, V in the numerator on the right side, and in the denominator, we're going to refer to that expression as impedance. Impedance refers to the overall resistance introduced by the resistor, inductor, and capacitor. Let's replace inductive reactance, XL, with omega subscript D times L, and let's replace capacitive reactance, X sub C, with 1 over omega subscript D times C, and you can see we get another expression for the tangent of the phase angle phi. This is very useful in some circumstances. If the inductor's reactance is greater than the capacitive reactance, the phase angle is greater than 0, and we say this is a mostly inductive circuit. If the capacitive reactance is greater than the inductive reactance, the phase angle is less than 0, and we say the circuit is more capacitive than inductive. If the capacitive reactance equals the inductive reactance, the circuit's phase angle phi equals 0. This is a special situation known as resonance. Resonance is a pretty big deal. It's often desirable to have a circuit at resonance because the net resistive effects due to the resistor, capacitor, and inductor are minimized. At resonance, the driving frequency from the EMF source equals the natural frequency of the inductor and capacitor, 1 over the square root of LC. Study this graph very carefully. It's basically saying when you run a circuit at resonance, you get peak amplitude response, which is, again, usually the goal. At a frequency lower than the resonant frequency, you have a mostly capacitive response, and at a frequency greater than the resonant frequency, you have a more inductive response. Quality factor refers to the relative sharpness of the power produced at resonance. A really large but narrow spike, like you see here at the top, might be desired if you're designing, say, for example, a radio reception circuit. You wish to tune to the station 98.7, for example, which means you want a really sharp response at that frequency, and you want to have all other lower and higher frequencies ignored as much as possible. Power in AC circuits is obviously a big deal. We start with P equals I squared R, which we've used a lot. Apply some calculus and coin a term known as root mean squared, RMS. Here's an expression for RMS current, average power, RMS voltage, and RMS EMF. This last bullet is pretty informative. When we're looking at AC, anytime we mention values for current or voltage, we're really referring to the RMS values. Power factor is basically a measure of how well the voltage and current are in phase. At resonance, phi equals 0, so voltage and current are perfectly in phase, and the power factor depicted by cosine of phi would equal 1, which is the maximum value possible. Here's some more detailed interpretation of the meaning of a power factor of 1. I think this last bullet is especially interesting. Power companies place series connected capacitors throughout their transmission systems to get these results.